Hello everyone. Today we'll talk about the solution to the problem take gifts from the richest pile. This problem is classified as easy because the constraints in this specific version allow us to use simple, unoptimal solutions. But since it's part of the category of problems that I like to call staircase problems, there are two canonical approaches that we should try when we are trying to get the optimal solution, which is either binary search on the result, binary search on the answer, or using a heap and simulating just all the case steps step by step, because the heap is exactly the data structure for us. Whenever we have a situation where at every step we choose something that is the biggest or the smallest, and we do something with it, we reduce it in this case, and we put it back, so we leave behind the square root of the number of gifts. So we put it back after that modification, and the number k, the number of steps, is not that big, so we can afford to just iterate over all the steps. Then heap is perfect because the heap, what it allows us to do, is it allows us to get this maximum value in a set of values that we have, and that's the only thing that it's supposed to do. So, in order to simulate the process, we have to maintain this set of gifts, take the best, take the biggest one, and replace it with the floor of its square root. And at the end we take the sum of all of them. So we'll be having our gifts. Let's skip the heap for now. And for every step we have this line gives us the maximum gift and removes it from the list. And this line pushes back into the list our value of v to the power of 0.5. At the end we have to just return the sum of gifts. And now here's how this solution changes because we are using a heap. You probably have seen those negative signs. This is a standard, pretty ugly, but in a sense idiomatic way of working with heaps. Because we are given functions to work with heaps in the heapq module, and the heap that the heapq module creates by default is a min heap. So it'll give us the values that are the smallest in our set. So if we want to have a max heap, and we're only given functions that work on a min heap, then we can just add a negative sign before every value that we have. Because now the value that was the biggest in our set, when we put a negative sign in front of it, it becomes the smallest in the set after that transformation. So this is exactly what this min heap will give us. So instead of working on gifts, we'll be working on a copy of gifts that's just minus v, for v in gifts. We have to make a heap. We can either add elements one by one, so we could just start with an empty list and add minus v for v in gifts step by step using heap push. It's better to use heapify because every heap operation takes logarithm of n time, but if we have an array that we want to heapify, then we can do it in linear time. If you're not that familiar, then feel free to look it up because a heap is a simple data structure and it's pretty nice that you can do it in linear time instead of just for every element adding it in naive fashion. So we need to call heapify on our list. We wouldn't need to if the list was empty, but here we want to start with all the gifts that we have already. And now this is a heap. Gifts is a heap, but it's still a list. And at the end we'll be just going through all of that, summing it up, and adding and returning the result, of course, with a negative sign in front of it because we're maintaining everything with a negative sign. So we want to return minus sum of gifts. But this is still a normal list, and the only thing that we get, and the only thing that essentially is part of the interface, is that gifts of 0 is the smallest element on that list. And that's what those operations will always maintain. They'll be maintaining also some other things. Feel free to look at the specification for what a heap is. And so to get the maximum element, so the line 6, we just use the function heap_pop. It removes and returns the minimal element. So in our case, we put the negative sign and we get the maximum element instead. And then we put back the element, we just do heap push. So you can see that you can just add heap, add negative signs when needed, and suddenly a solution that was quadratic turns into a solution that's n log n, or in this case k log n, because every operation takes log n time, and we have k operations. And this is a straightforward simulation, as I mentioned. maybe it's possible to solve this problem using binary search on the answer, feel free to try to do so. Well, it's certainly possible to do it. I'm just not sure if it's possible to do it directly or if you have to skip. For instance, if you assume that k is very, very big, that binary search allows us to skip the majority of steps, but still maybe at the end we have to perform some simulation manually. But it's also an approach that just combines the two, both the heap approach and the binary search approach.